A warm welcome to the 6:30 talk of today. It's one of the many things I love Congress for is the bold programming. Normally this is the arts and culture stage and society stage, and so I'm very excited that there's also a security talk today happening. And our next talk, Let's Break Modern Binary Code Obfuscation, is going to be translated into German. Es wird auch auf Deutsch übersetzt under this address, streaming.c3lingo.org, which should also appear on the screen now. Wonderful. And from Bochum, I'm going to welcome now Tim Blatzitko and Moritz Kontek, and they're going to explain to us how you can deobfuscate code without looking at the code, but only its behavior. A warm welcome and a lot of applause.
Thank you. First, can we enable the TV down here? Technique? Could you? Well, hi. So, welcome to our talk. So, we are, Moritz and I, are two PhD students and reverse engineers at the Ruhr-Universität in Bochum, Germany. And we discuss and in our daily work, we do reverse engineering and things like that. And as part of one of our academic projects, we started with program synthesis for binary deobfuscation. And then, thank you. And so this is basically the more technical version of our academic talk that we presented and publicated at Usenix Security this year. So in the first, Moritz will talk about code obfuscation techniques and deobfuscation techniques, and I will later join with program synthesis and how to apply that. Thank you.
All right, thank you for the introduction. Okay, first things first. Why do we want to obfuscate code in the first place? So to settle the scene, it's important to note that we cannot really prevent reverse engineering attempts, but rather we seek to complicate them, at least to some degree. Reasons why we would want to do so are mainly intellectual property and the protection thereof. So like if you get some super secret algorithm which gives you some competitive advantage over some competitor, you can just protect it and just have a head start to this other corporation or something. Another reason why we want to obfuscate code would be malicious payloads. So we want to make them harder to detect so that analysts are not easily able to create signatures for those, and the malware lives longer without being picked up by an AV. And the third, I think, most interesting case is digital rights management, where software, especially AAA games, larger games, are just obfuscated in order to prevent cracking attempts and illegal distribution of the game itself. And especially in the context of digital rights management, there's a very fitting quote which settles the scene as to what we can expect from code obfuscation. It's from Martin Slater of 2K Australia and was issued regarding to the release of BioShock back in 2007. And he told us that they achieved their goals because they were uncracked for 13 whole days. So apparently, we cannot really prevent obfuscation. We can just make sure to make the software withstand cracking attempts at least 13 days, which is about the time in which the game distributor makes most of its revenue. Okay, how do we protect software? So there are different approaches to protecting software, some better, some worse. For example, we can just take a look at the software that's been used to analyze the programs itself, like Olly debug, like disassemblers, and so on. And one idea that comes to our mind is just to abuse shortcomings of these tools. So if we know Olly debug crashes due to some code analysis part of a specific FPU sequence, we could just issue that and make all the debug crash. Or similarly, if we get some process dumper, which is relying on fields of the PE header and memory, we can easily confuse them and just render these tools unusable. Another approach that's very popular is just to detect the environment the program runs in and check if we are running in an application in an environment that gives us information about the presence of a debugger. So there's some capability by the operating system, for example, the being debugged bit in the PEB, which is being set if a debugger is attached. Similarly, there are more low-level tricks we can abuse, or some operating system internals, which allow us to somehow detect the presence of a debugger and then just debug execution and to just prevent any reverse engineering attempts. However, both techniques have the drawback that first, they are, once you know how they work, they are easily fixed. You can just patch your tool, or you can just circumvent the anti-debugging tricks by just supplying the correct values. Also, if you go to Google and just search for game doesn't start debugger detected, you get over 6 million people complaining that they cannot run their latest AAA game because the anti-debugging technique that you might have, which might have worked reliably on Windows XP, doesn't really hold up on Windows 7 and issues a false positive. So benign customers cannot really use their game, cannot really play their game because the debugger detection was faulty. So let's set up some requirements we need for code obfuscation. An important one is that we want the code to be semantics preserving. So the mere fact of protecting the application should not change its observable behavior. So we do not want the game to break only because we want to protect it. A second point, we want to avoid external dependencies, at least in the context of our discussion here. So there are various attempts to outsource data, like on the internet, on an internet server, on a USB dongle, or on other separate media. But we are mostly interested in techniques that protect the code only. So we got a white box attack scenario where the attacker has everything he needs to attack the application at his or her hand. And finally, the most important point probably is that we want to employ techniques that are easier or way easier to deploy for us than for the reverse engineer to attack. So the anti-debugging tricks we've seen, or also the shortcomings of the tools which we can abuse, they are more or less effort 101. Once you know how it works, you can easily bypass it. But we want to employ techniques that are easy to deploy for us, but they're very hard to attack by other parties. Okay, coming to code obfuscation techniques. One technique that's been used in commercial protection engines is what is more known as opaque predicates. So consider this rather easy CFG on the left side. So we got some application with a linear control flow graph. If we now insert what is known as opaque predicates, the problem looks vastly more complex. So we got more branches and control flow which we have to track, and we have no clue that the underlying program in fact is very simple. Let's zoom in on one of those predicates. Okay, so we got a bit of code, we got a true branch and a false branch, both branching to a different basic block. So if we're just looking at this, we might come to the conclusion, okay, we don't know which branch is going to be taken, right? However, it turns out that this is what we call an opaque true predicate. So in this case, the true branch is always taken, irregardless of the behavior here in the predicate. So what's happening here is that we've got an opaque predicate on top. This is the whole block, which is just constructing a predicate based on an opaque value, like the return value of the API call getCurrentProcess. And if you've ever worked with the Windows 8 API before, you might know that getCurrentProcess always returns a constant value, namely -1. So by just issuing this predicate, we make sure that we always take the left branch. The right branch might point to that code or to other point to confuse the reverse engineer, but at runtime we always take the left branch. Similarly, there are opaque false predicates, which just invert this condition and follow the false branch. And there's another flavor called random opaque predicate, in which we branch upon a random value. This means that we can potentially at runtime follow both branches. So the challenge here is that we have to make sure that both blocks or both paths that follow have to be semantically equivalent, because the program breaks otherwise. However, it is also a challenge to ensure that it's not easily detected by the attacker that both branches are in fact semantically equivalent. Okay, recapping on opaque predicates, obviously they increase the complexity of the application. Also, they can be built on hard problems, but what is most important is that they force the analyst to encode additional knowledge that either the analyst himself has to know it, or he has to just extend his tool to know maybe about the Win API, know about FPU instructions, know about arithmetic identities, or some other hard problems that he all has to encode in his analysis tool to provide reasonable results. So they are hard to solve statically. However, if we now opt to only look at concrete execution traces, so we just let the application run and look at concrete values, we note that opaque predicates are essentially solved for free for us. So this is good to keep in mind. Another very interesting technique that has also been deployed in, I guess, every major copy protection out there are what you call virtual machines. So take, for example, this native code on the left. We've got some loop here and some x86 code. And let's just assume the loop here is our precious intellectual property we want to protect. Obviously, we can use our common tools like disassemblers, like IDA or OLI-debug, to look at this code and reason about this code and get to know what this code does. So the idea here is to replace the code on the left with something our common tools cannot understand. So what we're doing, we're just getting creative, and we're just making up an entire instruction set, as you've seen on the right. So VLD, VPOP, instructions that are not known in this way by any other architecture. Full with new registers, with new encodings, and so on. And both the native code and the new instruction codes are semantically equivalent again. What you're now doing is just replace the native code by a call to what you call a virtual machine, or like also known as interpreter, which is basically a CPU in software, which just lets you run the imaginary architecture we've thought about. So if we now try to take our common tools like IDA or OLI-debug or some other tools to just analyze this code, it's not really viable anymore because we don't because they don't know about our made-up architecture. But we still have to make sure that the transition from native code to our virtual instruction here goes seamlessly. And to this effect, we have to look at the components. So there are three core components to a virtual machine. So mainly we got VM entry and exit. And what they do is just performing the context switch from native to virtual context and back. So the entry just copies the native context, let's say registers and flags of the native architecture to the virtual context, and the exit copies them back to the native context. Usually the mapping of native to virtual registers is 1-to-1, which makes it a bit easier. Then we got a traditional fetch, decode, execute loop, like in a traditional CPU. And what it does, it just fetches and decodes one instruction and forwards the virtual instruction pointer accordingly. Then it looks up the handler, which defines the virtual instruction in what we call a handler table here on the right, and just invokes this handler, and the handler goes on to actually execute the instruction. So as we've seen, the handler table is just a table of function pointers indexed by opcode, and we have at least one handler per virtual instruction. And each handler then just decodes the operands, operates on them, and just updates the VM context accordingly. Okay, so this is an example of a unobfuscated version of a popular VM obfuscation, and we might be able to make out these components here. So on top, we see the VM entry. So this is we're coming from the native code, calling into the interpreter, and here we're just switching the context to the virtual context. We're initializing the virtual context. Then we're at the VM dispatcher loop, which just looks up the current virtual instruction in the handler table, which in turn points to the individual handlers you see here below. So get direct reference to these handlers, and the handler then update the virtual context and branch back to the VM dispatcher. Eventually, we end up at the VM exit handler, which just performs the context switch from virtual context back to the native one. Okay, taking a closer look. In RSI, we have the virtual instruction pointer, and in RBP, we got the VM context. So you see that the VM dispatcher, all it does is just taking 1 byte of memory, increasing the instruction pointer, and looking up the corresponding handler and jumping to it. It might jump to the no handler, as seen here. And as you can see, it just reads out of the virtual context, performs some semantics, and then writes values back into the context, and finally jumps back to the dispatcher to execute the next virtual instruction. Okay, so this is rather simple and easily understandable. How do we harden this whole concept? For one, obviously, as we've seen, the handlers are simple. There are only a few instructions and they are easily understood. What we can do here is just apply traditional code obfuscation transformations to make analysis of them harder, like substituting operations, inserting opaque predicates, inserting junk code, and so on. So on the right, you see some slightly more complex assembly listing than before. Another technique, imagine you only got 4 handlers in your virtual instruction set. You want to make it more complicated, more work for the reverse engineer. And what we're doing is just duplicating individual handlers to increase the workload for the attacker. So because the handler table is usually indexed using 1 single byte, we got up to 256 entries we can populate. So what we're then doing, just duplicate existing handlers to populate the full table, and then again use traditional code obfuscation techniques to hinder the attacker from easily finding out that 2 handlers are in fact similar. And again, here, we want to increase the workload to the attacker, who has now analyzed up to 256 differently obfuscated versions of the handlers. Another technique you might recognize, we here get the central dispatcher and multiple handlers, which all branch back to the dispatcher, which executes the next instruction. What we can do here is to omit this single point of failure and just inline the dispatcher at the end of each handler. So what happens here is that we don't have a central dispatcher, but every handler branches to the next version. In summary, we inline the dispatcher into each handler because a central VM dispatcher just allows an attacker to more easily observe what happens inside the VM. It's like recording every handler that has been executed. And the third technique, we can also get rid of the handler table actually, because the explicit handler table easily reveals all VM handlers as we've seen earlier, because it points to every single start of each handler. What you can then do, instead of querying the explicit handler table we've been lying around in memory, we just encode the next handler address in the VM instruction set itself. So this might look a bit like this. We get the opcode, the operand, and then somewhere in the encoding, we're encoding the next handler address. This has the effect that it essentially hides the starting location of each handler that has not been executed yet. With the handler table, we would easily see where every handler lies and can deobfuscate and analyze it. But with these indirect encoding, we can only observe those handlers that have been occurring in a concrete execution trace. Okay, going on to mixed Boolean arithmetic, which is another obfuscation technique, not so widely used in modern obfuscation yet. But to give you an idea how it works, just look at this instruction here, or at this term. So it looks a bit involved, and you might not be surprised when I tell you that there's a simpler version of this expression, which is a simple addition of the values x plus y. You might guess that even for this more involved term, there's again a simpler variant. Especially here, it's the addition of x plus y plus z. Okay, you might believe me that it's easy if you throw the first term and the second term in your favorite SMT solver, and you are able to prove equivalence. However, what is interesting, how do we get to the second term if we only have the first? So we can try to maybe apply Boolean identities we know from school or something, maybe arithmetic identities. Maybe we might even go so far as to draw a nice Carnot wedge map. However, it becomes evident that this doesn't really help us here. In fact, what we are using here is the concept of a Boolean arithmetic algebra, which gives us a ton of different operations that are in this algebra, like Boolean operators, comparisons, and even arithmetic operators. It's worth noting that the Boolean algebra also includes, that the mixed Boolean arithmetic also includes a Boolean algebra and an integer modular ring. And it is worth noting that no techniques exist to simplify expressions that contain both. We know how to reduce expressions in Boolean algebra and in the integer modular ring, but there's no underlying theory that helps us in easily tackling both at the same time. Okay, on to deobfuscation. In every deobfuscation scheme, or in every deobfuscation tool we've seen, we get to a point where we employ a technique at some point, which is called symbolic execution. So consider the handler here on the left. This is the NOR handler we've seen earlier. And we now want to reason about this handler. So what we're doing is we execute it, but not with concrete values, but with symbolic values. This looks like this. So we're just executing this move symbolically. We assign to RCX the value of the memory cell indexed by the register RBP. We can continue to do so. And we got the second assignment. Also, if we got a NOT operation on RCX, we just assign to RCX the negation of RCX, which is the same as the negation of the memory cell pointed to by the register RBP. And we go on, and where it gets interesting is this case, where we got a logical AND on RCX and RBX, which is the same like the negation of the memory cell pointed to by RBP, with the logical AND and the negation of the other memory cell. But because symbolic execution is basically a computer algebra system, it encodes some well-known identities from the Boolean algebra, for example. And in this case, it knows that this expression is equivalent to a NOR of both memory cells. We can then just continue with the execution. And again, here, the symbolic execution engine recognizes the next NOR. At some point, this works rather well, and we see that the core semantics of our handler here is just a NOR operation on two memory cells and storing the result in another memory cell. So apparently this works fine for this handler. But what can we do, or what is the result if we try to throw this whole concept of symbolic execution at a more obfuscated handler? Here's a rather simple example of an obfuscated handler. You might be able to make out some parts, but let's just throw symbolic execution at it. We see that we get a ton of information here, but the problem is we don't really want a ton of information. What we want is just the underlying semantic, which is rather simple. It's the NOR operation of two memory cells and the assignment to another memory cell. Also, let's try to throw this at mixed Boolean arithmetic. So we have this rather complicated mixed Boolean arithmetic expression, and now just simply compile it into a program, just like a binary program, and then run symbolic execution on this trace. What you get is this semantic, and it didn't really fit on the slide, so it goes on. And you might be able to make out, yeah, the resulting values in RAX, and we got this super complicated expression. And again, what we got here as underlying semantic is rather simple. So we do not want to have this complicated expression, we just want this more simple semantic here. So symbolic execution is nice because it allows us to capture the full semantics of the code we execute. Also, it's a computer algebra system, and as we've seen in the NOR example, it allows some degree of simplification of the intermediate expressions. However, the usability decreases to some point if the syntactic complexity of the underlying code increases. For example, we can introduce artificial complexity by just substituting instructions or just using opaque predicates or other schemes we've seen earlier. Or we can also increase the algebraic complexity by employing techniques like mixed Boolean arithmetic expressions. Okay, so it's obvious that we have a problem with syntactic complexity and we want to handle this somehow. So the interesting question here is, what if we could reason about the semantics of the code only, instead of having to fight about the syntax and just improving our tools to be able to cope with more complicated syntax? This leads us to the topic of problem synthesis, which Tim will tell you more about.
Yeah, thank you. So we have seen some limitations of syntactic complexity. So, but it comes in my mind, obfuscation is semantics preserving. That means it has the same I/O behavior, input-output behavior. So why not just using a function as a black box and observe what it's doing? So, for instance, we might for this just generate some random inputs, 1, 1, 1, and observe 3. And we note that down. And we do this several times more. So we store this one, and 20 others again. So, and then we don't look at the code at all, we just look at its I/O behaviors. This here. And then what we learn is that we learn a function that has the same behavior. So we might learn x plus y plus z. And the goal of program synthesis is to automatically learn these things based on I/O samples. So how do we do that? So we use a probabilistic approach. Basically, we have an optimization problem. We have a surface, something like that, and this thing has some deep points, some large points, and we have a global maxima top there. And the global maxima is a program that has exactly the same I/O behavior as our black box. And we have a concrete value for each point on the surface. So the closer we are to the global maxima, the higher is our score. And in probabilistic optimization problem, we basically start with a minor score and just increase until we find the global maxima. How we do that is an algorithm that is based on Monte Carlo tree search. Basically, Monte Carlo tree search is one of the main reasons why AlphaGo last year was able to beat world-class human Go players in computer Go. So let's get practical and let's just synthesize A plus B modulo 8. We first somehow have to define how we generate programs. Well, we define a grammar. We have a non-terminal symbol u. Non-terminal means that we just can replace it with other symbols. So, for instance, we replace u by u plus a, or by u plus u, or by u times u, or by a or b. We say that a and b are our input variables. We cannot derive them any further. So, therefore, we have a candidate program, something as a, b, a times b, a plus b, b plus b, and so on. Contrary, an intermediate program is a program that contains at least one u, so we can derive it further. So, and with that, as a foundation, we do Monte Carlo tree search. We start with an empty tree that has just the root as root node, the u. And then we randomly apply the rules of our grammar. So we derive A. A in this case is a terminal program, so it cannot be derived further, so we can give a score to that. Because we are in a probabilistic surface, we have to score things. And so how we calculate the score, it doesn't matter now, we come to that later, just we give it a score. And then we derive the next thing, B. And also there, we give it just a score. This time, we derive u times u. So we cannot give it a score since we have an intermediate program. What do? we do something that is called random playout. We apply the rules of the grammar randomly and replace the U until we get a finite program that we can evaluate. So we have something as A plus A times B plus A and give it a score. And then we do the same with U plus U. Here again we have intermediate program. We derive something, score it, and go back. Now we don't have any further rules to apply. What we then do is we choose the best child node in a probabilistic manner. In this case it is U times U. And do the same thing again. We derive some expression, do a playout, give it a score, go back. Now each score basically represents the average score of all its children's scores. So in this case, we had a new score here, so we just update this one. And we go back. Again, we choose the best node, we do a derivation step, and so on, go back, update, choose the best node, play out, score, update, and so on. So now here, U plus A, we have a really high score. U plus B, we have a rather low score. And we want to synthesize A plus B. This means that U plus B had a bad playout and that U plus A had a good playout, because here the score is better. So we update this and go back. So we again choose this node, go back and go back. So as you can see, we always explored this area more than that. The reason is, well, because U plus U seems to me way more promising than U times U. However, we just have some probabilistic behavior. That means we sometimes explore also different ways just to get to know if we might miss something. So in this case, we would normally choose U plus A again. But we just decide to do that. We do a playout, we give it a score, and well, it wasn't really good. So because of that, in the next step, we go back to U plus A. Then we derive B plus A, and so we have a final program. We cannot derive it any further, so we can score it directly. Okay? We give it a score of 1. Why 1? Well, because B plus A has exactly the same I/O behavior as A plus B. So in other terms, we are finished with our program synthesis part. Okay, how do we score some values? How do we calculate something? Basically, what we do is we generate a random playout, we generate random inputs, and query our black box, and observe the output. So 2 plus 2 is 4. And now we use the same inputs and query our intermediate program and observe the output. Then we calculate the similarity of these twos and get a score. Similarity, I will come back to this on the next slide. So just we compare somehow the similarity. We don't do this only for one input pair, we do it for many. So we do this, we do it for this one. In this case, we have the same output. That means the similarity is 1 because it's exactly the same. And we do it several times more. And finally, our score for this node is basically the average score of all these similarities. How do we calculate the similarity? Well, we are operating in the bit vector space, so we compare the similarity of bit vectors. In other terms, we can compare if they are in the same range. So we have a look at the trailing zeros or ones and at the leading zeros or ones and count how many are the same. Then we can still compare how many bits are different. This is the Hamming distance. We use that, for instance, for something as overflows in terms of addition or XOR operations and AND operation and things like that. And then we still have A plus B or something like that without overflow, where we can have a look at how close are two values numerically. So basically the distance. And we use these metrics to tackle these different behaviors of the bit vector space, such as overflows and things like that. And we take, again, the average of all these metrics. Okay, how do we use that as a core to synthesize obfuscated binary code? So basically what we do is that we have an execution path, perhaps obtained from an instruction trace, perhaps from static analysis, whatever you want. And we somehow emulate it and observe indirectly inputs and outputs. We say that everything is an input which we read before we write to it. So in this case, these are the two memory cells top there. And everything is the output in red that we write lastly to. So for instance, the RBX is not modified anywhere, so this is an output. The same for RCX and things like that. And then we treat this again as a black box, generate random inputs, and feed it into our black box and observe the output. In this case, RBX. So we do this many times, so something about 20 or 30 times. And then we synthesize this output. And then we learn that RBX is not M0. And M0 is here, in this case, the first memory cell. We do the same for RCX and learn that this is basically the NOR of these operations. And finally, we do it for this one. And also there, we learn that this is a NOR. To conclude, we learn the semantics of the two NORs and the negation top there. What we don't learn in this handler is the pushf operation that is flag-based and the flags that are written back into the memory cell pointing at RBP. Why don't we learn that? Because we don't care. So basically, we designed our grammar in such a way that it just abstracts higher level semantics, ignores bit level semantics, and just abstracts higher level semantics. Or in other terms, we don't consider flags as any sort of input. Okay, we do random sampling about a code. What is if there's a branch that may be conditional? And we feed in random inputs. Well, we might trigger some different behavior such that the emulator decides to choose another path. Well, what we do here again is we just ignore the flags and we force the execution to go the path that we observed. So if we want to go to A, we just force it to go to A. If we want to go to B, we force it to go to B. So how do we implement something like this? Basically, you have lots of different opportunities. What you need is some code base that you can somehow execute code. For instance, emulate it as in Box or in Unicorn engine, or you can do it with dynamic binary instrumentation as in Pin or DynamoRio. What you also can do is you can just translate it into intermediate language, symbolically execute it, and evaluate just the symbolic expressions while feeding it with concrete inputs. But normally this is much slower, especially for large constraints, as you've seen it before. But in general, it is possible. What we did is that we implemented everything in our framework that we called Synthia. Basically, Synthia is a program synthesis framework for code obfuscation. It is written in Python. It performs random I/O sampling for assembly code based on the Unicorn engine. And it also implements MCTS, also Monte Carlo tree search-based program synthesis as a core. We published it under GPL version 2, and this is the link where you can get it. So we will just do a quick demo. So first I will show something about the program synthesis itself. Basically, we define an oracle that is a function that we treat as a black box that we use for I/O sampling, and what we want just is to synthesize x plus y plus y. So we just run it, and what you can see here is that we start with different nodes, that we try out different things, and always assign a higher reward to this. And you also see, oh, in this case, it somehow learned that there must be a lot of additions, and at some point, we get something like that. So this is basically V1 or V1 and V2 and V2. So this isn't the simplest form, but it is simple enough such that we can easily simplify it to something like 2 times the input plus 2 times the other input. So we can do that another time, and we might choose a completely different path, because it's all probabilistic. Perhaps one playout was better than the other, then we choose another path. It might take up to 5 seconds, up to 1 minute, so it basically depends how the quality of our inputs, how we choose a path and things like that. But at the end, we will mainly reach our goal. If not, we just start it again. So the first one, it took nearly 20 seconds, now it took 24 seconds, and you see now we have a much less obfuscated version in our non-simplified form. So it's okay. How do we use it for simplified code, to synthesize obfuscated code? Let's have a look at the source. This unobfuscated, top there, this is the plain code. Basically, it takes 5 inputs, just performs an addition and a multiplication and returns the value. Note, this is a function. That means our final value, the return value, will be stored in EAX. And we obfuscated it with Tigris in MBAs, and we get something like that. This is a little bit longer. So, and then we compile that and get some assembly listing. That basically is about 760 lines. So we don't symbolically execute it here because it would be really much of time. Instead, we just learn it. What we do is we just random sampling input. So we give it by basically a code file. This is our instruction trace. We define the architecture. We do, well, let's take 20 random I/O samples, and we write it to an output file. So you see, this were only less than 5 seconds. So if you look at the file, what we see is that we have different outputs. Here, this is one output, this is another output. We basically have 18 outputs because we start counting at 0. We are only interested in EAX, so we will just synthesize that in a few minutes. And you see, we have here our 5 memory inputs, our parameters for the function, and also some registers that were treated as input. Okay, so what we then do is we just define in our sample synthesis. This is a wrapper around MCTS. This reads basically the input file from before, and here I noted 0 because we only want to synthesize the first output now. So we just started. It basically takes the sampling file as input and an output file. And this again, this might take between seconds and 1 minute, so it depends. So we are ready. We can have a look at the result. You see, this is the output. The top non-terminal is some integer mal some integer that have not been further derived plus a concrete variable. The best top terminal, so the best program that cannot be derived any further, is a memory cell times a memory cell plus a memory cell. And so this is our final expression. Basically, we learned that the whole semantics is the first memory read times the second memory read, times the third memory read, plus the fifth memory read. So, okay. Coming back to our slides. How can we use that to break virtual machine-based obfuscation? A quick reminder, the goal of VM-based obfuscation was to introduce a new CPU scheme that you can't analyze easily with your tools. You have to manually reverse engineer all the handlers and things like that. And well, one simple thing we can do with that is just learn the semantics of arithmetic handlers, such as if the semantics is an add or nor or something like that. So Moritz discussed 4 different hardening techniques, and we will talk about how we can break all of these. So the first one was obfuscating the individual VM handlers with more complex obfuscation schemes. Then just duplicate handlers and somehow transform them such that they don't look the same. Then we don't have no central VM dispatcher, so we don't have an FDE loop. Instead, each handler inlines in concrete the calculation of the next handler. And then we don't have any explicit handler table. Okay, what you see here is a handler of Timida. It looks quietly more complex, and you don't easily see, also not with symbolic execution, what this is doing. Well, if we ask Cynthia, it says, well, the semantic is that it is an addition of the 13th and the 14th memory read, and it is stored into a 64-bit value. Okay, solved this problem. The other problem, duplicated VM handlers. Assume we have a handler table where we can see each handler, or we have an instruction trace where we know where each handler is located. So given we know where handlers are, so how can we learn duplicated VM handlers? Well, at least we learn its simple semantics. We can learn based on our grammar if it's an add, if it's an XOR, if it's a sub, if it's a shift left, and things like that. And of course, we can find duplicate for free because we learn the semantics. And if they are the same, we learn it. Okay, so coming back to our Timida handler and no central VM dispatcher. Have a look at the end of the handler. Let's zoom in. Basically, this plus the code above there is the code to calculate the next handler address. So this calculation is a little bit too complicated for our synthesis part, so it doesn't tackle our semantic approach, because we still learn the semantics of the handler. And since the semantic of the next address calculation is too complex, we just don't learn it. And one other thing, have a look at the jump RBX. One advantage or disadvantage, depends how you see it, of inlining something like that is that we have a hard heuristic how we can find the end of VM handlers. Basically, they end with a return or with a jump RBX. So basically, if we split an instruction trace at indirect control flow traces, control flow transfers, we split it into the separate VM handlers. This helps us for our fourth part. We don't have an explicit handler table, so we don't know by static analysis where each handler is. So what we can do is we just execute it and we observe the instruction trace. And then we have something like that. We just then apply the rule from above. We split everything where we observe indirect control flow, and we get something like that. And as it points out, each color is a different handler. So, and then we can take these single components and just synthesize it on their own. And in this case, we automatically learned large portions or large things of the instruction trace. And we have a built-in semantic disassembler for free for the new architecture, if you want it that way. So, but we can say you a lot of things, just try it out your own. We released our code, and furthermore, we released all of our samples. So just feel free to use it and play it with around. So, to conclude, we talked about obfuscation techniques, mainly opaque predicates, VM obfuscation schemes and hardening, and mixed Boolean arithmetic. And of course, they all can be used together. And they all are mainly, it's all mainly the same if we work on the obfuscation on the instruction trace level. So then we discussed about symbolic execution and for syntactic deobfuscation. And we saw that it's really great, but it has some drawbacks if it is syntactically too complex. So on the other hand, we asked us then, what about not looking at the code level, but instead looking at the semantic level, using the code as a black box to obtain I/O samples and learn something different. So this is program synthesis. And a final reminder, you find everything in our Git. Thank you very much.
Thank you very much indeed for this creative solution to an existing problem. We now have about 10 minutes for Q&A. You know the drill. There are 2 microphones in the middle and 1 to the left. Please line up. Also, Signal Angel, do you have questions from the internet? Okay, none. And are there questions from the audience here? 1, okay. In the back, please.
All right. Yes, I was wondering...
And please try to go out silent.
It's all right.
What?
Okay, do you still hear me?
Yeah.
Okay, I was wondering if one takes a look at these obfuscation techniques, wouldn't it be possible for a closed source operating system to just prevent any debugging of code? So say we could encrypt the code with some key that only the operating system has access to and then only shovel it to a protected memory area?
Well, what you might do is that you execute it inside a virtual machine or something like that. Assume you can do that, and you can take memory snapshots and memory breakpoints at different points of execution. What you can then do is, if you know somewhere in combination with reverse engineering, that at this memory area now lies an deobfuscated code, decrypted code, because you know it just was decrypted because it is used for execution now. You can take a memory snapshot and dump the code and then feed it into something like that.
Yeah, also to add up on this also, kind of a non-technical argument to make here, because all the, like the argument we had on the slides, if you try to outsource your code, this is like a similar scenario, because to have hard guarantees on that, you might want to have like some HSM or some other hardware mechanism to enforce this, which might not always be feasible. Like imagine having a corporate environment where you need to supply USB dongles or something, which might not be which might be in violation of some corporate policy. So we've been looking only at things we can do in a white box attack scenario where the attacker has everything he needs to analyze the code, which is the most non-restrictive scenario here.
Next up, mic 1.
Hello? I would like to ask, these techniques also seem to be very useful for code optimization in compilers. Has any research been done in this direction?
Yeah, lots of research. So basically there is one big project, this is called Stoke. This is from the Stanford guys. They do stochastic program synthesis for super optimization. And this was also one of the inspirations for us to use a stochastic synthesis approach.
Thank you.
Do we have a question on the left also?
Yes.
Okay, yeah, then you go.
So if I understood you correctly, then you focus primarily on arithmetical functions or on arithmetical expressions. So
Yeah.
can't you simply use techniques of numerical curve fitting?
Well, this might be possible. We haven't looked into that, but we mainly looked at that because we needed something to evaluate our approach. So we designed our grammar to learn something like that, but we are free to choose any more complex grammar or learn much more deep expressions. So was just obvious that we wanted to de-obfuscate was rather easy from the semantic level here, but the approach is much more powerful.
Okay, thank you.
I heard that the internet is also still awake, and we have a question from the Signal Angel. Please, Signal Angel.
Yes, we do. Have you tried synthesizing intermediate representations?
No. This is in general possible because Rolf Rohls and others did some work on that, and there's no reason why you cannot do this with that approach. But we basically, it depends mainly on the grammar, what you want to synthesize, and on your I/O pairs. So if you design the grammar that way that you want to synthesize some IR, you can do it.
Because we're moving so fast, I think we still have time for one question of number 2 in the back.
Hi, does this work? Yeah. Okay, so you've been using kind of fancy words, but in the end, I think what you're doing is essentially an optimized search for an expression that looks like it gives the same semantics.
Yeah.
And now I'm wondering what is it that makes you believe that this is faster than just randomly trying expressions? So why do you think that the child nodes in this MCTS tree are some indications are somehow better if the metric of the parent node is better?
Well, basically we have a really large search space. So for VM handlers, if you have just A plus B, this is rather simple in semantics. But normally we have something about 20 to 50 inputs and several outputs, and we have not only just multiplication or something like that, we have a much larger search space. So we have 8-bit input variables, we have 64-bit input variables, we have downcast, upcast, zero extents, the whole grammar as bit shifts, left shift, arithmetic shifts, and XOR, and also modulo and division and things like that. So we have lots of components such that we need, so that for A plus B, something like that, you are probably faster. But if you take A plus B plus 4 plus C, you are not that fast anymore. So we have a really large search space, and if you use some kind of guided learning, this helps much.
Final question, Mike 1.
Hi. So it looks to me a very interesting work, but my only question is, what if the function you're trying to obtain, what if the similarity function does not respect what the obfuscated code is doing? What if, for instance, it's not the case that the similarity increases the more you get closer and stuff like that? In shorter terms, how would you break your own system as violating the assumptions of your similarity function?
Well, of course, if you just make it semantically harder, for instance, it won't work at some level anymore. But the observation, so what you can do, for instance, is if you apply some form of local encryption or something like that, this might break, or this will break, for sure. But one of the observations we made is this isn't done yet. So, and this was a really interesting fact. And also one of the main things is how you choose the boundaries of where you start and where you end with your window that you analyze. And there can also be, in this case we had a look on the handler level, but there's no reason why not to combine several handlers or split into handlers in half or things like that. So there might also be ways by choosing window boundaries to tackle this again.
Okay, thanks.
Okay, those who didn't get a chance, I'm sure you can approach the speakers next to the stage once they leave. Again, thank you two very much for the interesting talk, and let's conclude this with a round of applause.